video, I want to start digging in a little deeper into the kinematics of motion. And the simplest form of this that we can start with is 1D particle kinematics. So what I mean when I say 1D particle kinematics is that we are looking at a particle, which you can think of as just a dot, and we only are going to think about it in one direction. So one-dimensional motion. So we'll define this direction as x, and we're going to consider a particle that's moving along to the right on the screen here in the x direction. So I might define some various points of this particle's motion. So let's call this initial point 0. The particle moves to the right in some amount of time, ends up at position here, which we'll call 1, this next position, moves on, ends up at another position at a later time, which we'll call position 2. So the particle is traversing from left to right, from position 0 to position 1 to position 2, and while that's happening, some time has passed. So we would define the position of this particle at any given moment as x being a function of time. So I've written that in a mathematical notation with x as a function of t. So as a particle moves along from one position to another position, we can also write this as delta x. So delta, the uppercase delta here, indicates change. So this means a change in x. So as I've gone from this position on the left to the position on the right, my x has changed. At the same time, we have had a delta t that has occurred. So some time has passed as the particle has moved from left to right. So over here in my initial position, we would say, let's call this initial position x and initial time t. And the particle moves to the right and ends up at some new position x plus delta x and some new time t plus delta t. So my initial position x and my initial time t have undergone some change, which is the addition of delta x and delta t respectively. This change in position and change in time we can use to calculate the average velocity of my particle. So if I'd simply take change in position over change in time, I would get average velocity. And average velocity is going to have units, velocity units of, for example, meters per second, or feet per second, or inches per second, or millimeters per second. Some unit of distance divided by some unit of time. Miles per hour is another example. Now, as this time over which I measure the position of my particle gets smaller, that velocity approaches the instantaneous velocity. So if I take, in mathematics, the limit of delta t as it goes to 0, so my delta t is getting smaller and smaller, and then of course my corresponding delta x would have to get smaller and smaller. So the limit of this equation, delta x over delta t, becomes a differential derivative of x with respect to t, and that should be fairly familiar, right? dx by dt. Sometimes we would also write this as x dot, where that little dot over the x indicates that I'm taking the time derivative, or the derivative with respect to time. Great, so we've got now a definition of instantaneous velocity that we will make use of. Now I can take this one step further. I can look at the same particle as it travels through space from one position to the next, and I can measure its velocity at some initial point and its corresponding time. As it travels from left to right, it could undergo a change in velocity while it undergoes a change in time, such that my new velocity is the initial velocity plus the change in velocity, and my new time is the initial time plus the change in time. Doing so, I can treat this in exactly the same way as we did in this previous case, which is to look at the acceleration, which we know as the change in velocity over a change in time. So I can write that in the exact same manner as I did before, as delta v over delta t. So now, if we think about our units, velocity up here we defined as having units of meters per second. That's still true. So delta v is meters per second divided by time, so it's per second again. So we get our expected acceleration units of meters per second squared, or feet per second squared. Now the same condition applies, that I can take the limit of this function as delta t goes to 0, and I get dv by dt, which I could write as v dot in the same way as I did above. I can take this a step further, though, to say, well, in terms of position, this is the second derivative of my position x. So I've also written this as x double dot as a way to express this in terms of position. So the double dot, the two dots over the x, indicate that I'm taking a second derivative of x with respect to time. Another way I want to look at this, acceleration, which I'm denoting with an a, is equal to dv by dt. I can take this dv by dt and I can break it up into dv by dx and dx by dt. Now, mathematically speaking, this is the exact same thing, right? Because if I multiply dv by dx by dx by dt, the dx's would cancel each other out, and I'd be left with dv by dt. So I haven't really changed anything mathematically in terms of what I'm writing. But the reason I might want to do this is because I can recognize that dx by dt over here is just velocity, right? So if I recognize that dx by dt is velocity, I can rewrite this expression as v dv by dx. And the potentially useful bit of information, or the usefulness of this expression, is that it doesn't contain time specifically. So if I'm able to measure the velocity at any given point, and the change in velocity and the change in x position, I can use that information to evaluate acceleration. And I don't have time involved in that expression. And that can be useful for me. We'll see that later as we go into it a little deeper. All right, thank you.